Greetings and welcome to my new calculus site. My name is John Gabriel. Excuse the patch over my right eye, but I am suffering from extreme pain and nobody knows why. Anyway, so what I'd like to do today is to discuss proportion, ratio, and number yet again, but from a clearer perspective even than what I have discussed it in past videos. So, without further ado, let's begin. Now, if C is the circumference of a circle and 2r is its diameter, is this here the same as this fraction here? What do you think? Well, let's see what the answer to that question is. So, first of all, we have to look at what the meaning of proportion. What is the meaning of proportion? So according to the dictionary, it's a part, share, or number considered in comparative relation to a whole. Now, that's not completely correct because a proportion cannot be a number. Okay, so proportion is originally derived from the description of magnitudes or sizes, and the confusion stems from a number of reasons. And so we'll take a look at each of these reasons in this video. The first one is that the ancient Greek text used the word analogia, which refers to magnitudes, not numbers, okay? So a rate in modern Greek is called pososto, which I don't even think there was a word for it in ancient Greek. Then secondly, there is much polymorphism in the Greek language. What does polymorphism mean? It means that it means many forms. So different concepts or the same concept with many forms. The word analogia is used to refer to proportion in one of its forms. Okay, so that's number two. And number three, magnitudes can be in proportion, but they're not numbers. Okay, so proportion is a geometrical concept that found its way into algebra. Okay, so it started off with magnitudes, okay, and then gradually it was transferred to algebra in a very confused way. Now, in book 5 of the Elements, Euclid defines magnitude in a circular way. He doesn't really have a good definition. He should say a magnitude is the concept of size, dimension, or extent, or just simply a magnitude is the concept of size. And in Greek, one would say that as to megathos είναι η έννοια της έκτασης. Okay, so what that means is that it's simply a concept, okay? It's not a number. A magnitude is not a number, as I've always said. The size genre that Euclid was referring to throughout the Elements is distance, okay? Not mass or density or anything else. In definition 3 of book 5, the ratio is again introduced using the word logos, which is a derivative of analogia. Now, what is a proportion exactly? It is a relation that any two magnitudes share. So for example, if you look at this blue distance and this red distance, well, they're not really distances. They're actually lines signifying distances because you can't really reproduce or construct a distance. They share a relationship. But what relationship? I don't know right now, and I don't care. But both of them, what we can say about both of these is that unless we compare them in a systematic way, we cannot arrive at some useful conclusion. So, if we look at these lines here, we could say that this blue line is to the smaller blue line as this red line is to this smaller red line, because this blue line happens to be exactly twice this little line, and this red line again twice this line. And so we can write that this ratio and this ratio are in proportion. They are not equal, by the way. They are not equal ratios. Otherwise, why would we write them differently? Okay, that's one of the reasons. So they're in proportion, but not equal. So we've learned about the first two reasons, the polymorphic use of the word logos or analogia, and the meaning of ratio and proportion. The third and last reason that causes confusion over the transfer of meaning to algebra is simply the fact that Euclid uses the abstract unit to generalize measure. Okay, so in book 7, these ratios morph into the numbers 2/1 and 4/2. Okay, meaning that 2/1 is the measure of this distance, and 4/2 is the measure of this distance. So since the abstract unit doesn't matter, the size of the abstract unit doesn't matter in algebra, we say that 2/1 is equal to 4/2. However, note that you cannot write this in algebra because these distances here are not numbers, right? So you cannot do that in algebra. Yes, in algebra you cannot do it. Now in geometry it wouldn't even be right because this vinculum here, this black line, this vinculum, is not part of a ratio, okay? We use a colon to signify it as a ratio. It's the significance and the difference is very important. So in geometry you could say they're in proportion using the tilde, but the correct form would be to say use a colon and don't use the vinculum. So this ratio is in proportion to this ratio. And if we had to look at algebra, then we'd put the measures of these distances over in terms of a vinculum, and we'd replace this with an equal sign in algebra. So if we have this ratio as a circle circumference to its diameter, and also this ratio as another circle circumference to its diameter, we could write that this c to diameter is in proportion to this c to diameter, but we could not write that this is equal to this ratio, okay? That this ratio is equal to this ratio. They're not equal, okay? They're in proportion, okay? So the incorrect custom in algebra is to write c/2r is equal to c/2r. But that's not correct because c/2r, c and 2r are not numbers in geometry. They're magnitudes, okay? So this here is completely wrong, okay? Now, when we do this in algebra, what we really mean is a rational number approximation, okay? Some rational number approximation. So for example, 3/1, which is approximately 3, and 6/2, which is approximately 3, which is not exactly pi, but it's an approximation. And that's all you have in algebra. There is no measure of that ratio, c to 2r. There's no measure of that. Okay, it's impossible to measure pi. So, and you may wonder why all this is so significant. Well, the reason is that the properties of arithmetic in geometry, because that's where they were defined, by the way, in Book 5 and Proposition 12, are for magnitudes, not for numbers, and they're transferred to algebra through a weaker form of geometry, they're transferred to algebra through the abstract unit, let me repeat that. They're transferred to algebra, which is a weaker form of geometry, through the abstract unit, whose size is irrelevant. Okay, and in algebra, we define number rigorously. We define number as a name given to the measure or a measure that describes a size or a magnitude. Okay, and to be even more correct, it describes the size of the antecedent part of the ratio, right? So, and this is where I talk about it. A number describes a measure of a ratio's antecedent part if and only if both the antecedent and consequent parts of a ratio have a common measure. Now, if you have c and 2r, there is no common measure, so there is no number that you can transfer to algebra, okay, that you can use in algebra. And such a divisor can be any magnitude in geometry. It doesn't have to be a rational number or what you've come to know as an integer or a whole number. It can be any magnitude. But in algebra, it must be a rational number. Okay, so both parts of this ratio that you see here are measured by this distance or this line. And so if we choose this line here as the divisor, as our unit in algebra, then we have the rational number 2/1. Remember that in algebra, again, the size of the unit is irrelevant. What this means is that whilst the measures 2/1 and 4/2 are indeed equal, we can write 2/1 is equal to 4/2 in algebra. The process of measure is different. 2/1 is a measure using the whole unit, and 4/2 is a measure using 4 of 2 equal parts of the unit. Remember, this denominator in algebra means the number of divisions of the unit. So number of divisions into equal parts. Be certain to read how number was realized. I don't want to go there right now. The link is here. I'll place a link to it in the details section. And that's pretty much it for this video. I hope you now understand why you cannot write C, the ratio of C to 2R. So the answer to this question is that this here is not the same as C/2R, because C/2R would mean that there's a number that describes C in this ratio. There is no number that describes it. So we call this pi, but this here is just a rational number approximation to pi. Okay, and it's not, strictly speaking, accurate. It's not accurate in the complete sense, and it's definitely not the same as the ratio. Very well, I'm out of breath and I haven't been feeling too great lately, so I'm going to leave it at that. This is the New Calculus channel. I'm John Gabriel. Till next time, stay safe and goodbye.